Today we're continuing our discussion of refraction through lenses by talking about the thin lens equation. So we're going to take exactly what we were doing before and put numbers to it so we can calculate these things. So for the thin lens equation, we have our convex lens, we have an object, and we have our image. It's a real image because we're outside of the focal length. And as you can see, this ray passes through this point. I'm going to call that our focal point. It's a distance of, we'll say, f away from our lens, and it refracts out parallel to this axis of the lens. This one passes straight through the center of the lens, goes through unrefracted. This one comes in parallel and refracts out again through that same kind of point, focal point, which is the exact same distance f away, still the focal point. For this kind of lens, we have a positive focal point. Things go through and refract through this focal point. Okay. Now, the other distances we have to worry about are this one. That's my object distance. We're going to call it di. And this one, my image distance, we're going to call it, sorry, that's do for object distance and di for image distance. So the relationship between all of these things is fairly simple. We've got 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance. That's not very useful to us. Most of the time we're looking for the image distance, so we're going to say 1 over our image distance is equal to, just simple math, 1 over f minus 1 over the object distance. This is how we're going to be able to predict where our image is going to be. So we have two examples to look at how this is going to work, and tomorrow in class we're going to try to put some trends together to see how this works. But one thing I want to point out is if we look at the object here and the real image here, we can see that the real image is smaller. This is diminished. It's gotten smaller as we've gone through this lens. Okay, it's shrunk it. It's also inverted. We also have rays actually crossing. Lenses magnify things or make things smaller. It turns out a convex lens is the only type of lens that can make things bigger. That can give us a magnification. So let's go through an example. Alright, here we have our object at this point C. We'll talk about that, what that means at the end. For this example, let's say that our object distance is 10 centimeters and our focal distance is 5 centimeters. Let's use the thin lens equation to predict where over here, because that's what di is going to be, what di is going to be. So 1 over the image distance is 1 over the focal distance minus 1 over the object distance. 1 over 5 minus 1 over 10. Well, we can't really do that, so 2 over 10 minus 1 over 5. And you can do this in your, 2 over 10 minus 1 over 10. You can do this in your calculator, but we get 1 over di is equal to 1 over 10. Which means my image distance, I'm going to take the inverse of both of these, flip them both over. My image distance is 10 centimeters. So that means that my image should be over here. And since it's on the other side of the lens, okay, my image should be somewhere there. Since it's on the other side of the lens, it's going to make it real. And that positive sign means the other side of the lens. That positive sign also means that it's real. The positive sign also means that it's going to be inverted. So if we do our rules, let's see what this gives us. If we draw a line coming in to to the lens parallel, we know that it has to go out of the lens. Oh, and this is going to be hard to do. Out of the lens through the focal point. And we know that if we come into the lens through the focal point, we have to come out parallel. And if we go through the center of the lens, and who knows how well this is going to work, if we go through the center of the lens, we go on unrefracted, which kind of gets me to this spot right here. Now, the center curvature, we're going to talk about that, is twice the focal length. If I have an object at the center of curvature over here, it shows up at the other center of curvature, and there's no magnification. And it's a real image. If I were to move this thing forward, we would see this object move farther away and get bigger and bigger and bigger. If I were to move this back, we would see the image get closer to this focal distance and get smaller and smaller and smaller. If you've got time, go back to the PhET demonstration from yesterday and look at that. We're going to look at one more example. Alright, looking at this example, we're going to have our object inside of our focal distance. So this time, let's make our focal distance 10 centimeters and our object distance 2 centimeters. It's going to be right there close to the lens. And let's look at what this says about our image. So 1 over our image distance is going to be 1 over our focal length minus 1 over our object distance. So getting a common denominator, 1 over 10 minus 5 over 10. And we get that 1 over the image distance is equal to negative 4 over 10. So the image distance is equal to negative 10 over 4, which is negative 2.5 centimeters. Okay, so that negative sign means that it is on the same side as the object. It's on the same side of the lens as the object. It also means that it is a virtual image. So it's going to be 2.5 centimeters this way. So we expect it to show up behind this guy. Well, let's look at how the light rays actually go through here. The first one is any light passing through the focal point hits the lens and is refracted out parallel. The next one is any light that comes in parallel to the axis hits the lens and is refracted down through the focal point. And the next one is anything passing through, that's right there, anything passing through the center of the lens goes through unrefracted. Now looking at these three, it's obvious that they're never going to touch, but when our eye sees it, it takes it and traces these back to where their origin might be. And that's exactly what we're going to do. So if we trace this back, and if we trace this back, this is where the image, this is where our eye will see the image. Now, we see that it's upright, so it's virtual. We also see that light rays don't actually cross here, they just get traced back. That also makes it virtual. And we see that it's on the same side as the object, and it's backwards a little bit. This is really all there is to using the thin lens equation. Combining it with the drawing gives a sort of clear picture of what's going on. So tomorrow we'll look at a few more cases of this and see if we can see some big patterns. So.